Hello everybody, my name is Damjan Jelic, and with my associates Barbara Malecic, Barbara Vodaric, Šurja and Maja Telešman-Pertenjak, we are attempting to estimate hail using lightning and radar data. We selected for this presentation a case study on 25th of June 2017. This work is done under the Svaldric project and is financed by Swiss National Science Foundation and Croatian Science Foundation. So on the 25th of June 2017, there was a plenty of convection going on in the region of Croatia, and in the continental part, which is covered with multiple radars, from which we are using a Bilogora radar. We can see that multiple convective systems combining into larger systems are actually passing over, causing a lot of severe weather within the observed domain. Actually, 58 records of hail were reported from the national network, hailpad network, ranging from 5 millimeters to 3 centimeters in diameter. For the same region, we also collected the lightning data from Linet network, centered it on the 3 times 3 kilometer bins, and from those bins we then computed what we developed within our group is a Eulerian-based lightning jump. So the idea of this lightning jump is to highlight those regions of storm. So this is a total lightning of one particular storm, to highlight those regions where this storm had most of the lightning activity. In sense, wherever we detect sudden increase in lightning activity, we call this place a lightning jump. And as you can see, within one particular storm, some regions can detect multiple lightning jumps, meaning that this storm within this observed area had increased its lightning activity several times. Generally, lightning jump occurrences are associated with the severe effects like wind gusts, tornadoes, hail, and heavy rain. So we are attempting to see how well is this trail of lightning jumps connected with the hail in this particular case. So to see maximum reflectivity of radar in upper figure, where the lowest value is 35 dBz, we can see that the whole continental part of Croatia is actually covered with a strong reflectivity, suggesting a lot of severe weather within those systems. The system generally moved from somewhere, let's say, southwest towards northeast, and started from around 12 UTC until the end of the day. The downside of the radar we were using is relatively a low scanning interval, which is 15 minutes. And we can see that since the storm is passing very fast, there are a lot of gaps in between the scans, which actually don't have any useful information. So this will influence the quality of our assessment. On the lower figure, we show the total lightning activity, which actually includes all flashes collected with the Linet network, including cloud to ground, intra-cloud, cloud to cloud. And we can see that some regions have a very strong signal in lightning activity, which is actually a consequence of multiple storms passing through this region during the whole day and producing the higher values of lightning. So if we put all our data in one figure, it looks something like this. So black points are showing hail pad locations, and the red points are showing hail pads which reported some type of hail. And the size of these red points is actually proportional to the maximum diameter recorded on that particular hail pad. Blue color indicates maximum reflectivity larger or equal than 50 dBz, while brown points are showing locations where we computed the lightning jump. Using this data, we actually computed contingency tables between hail pads and radar, and between hail pads and the lightning jump, and use some standard values like probability of detection, false alarm ratio, bias, critical success index, hydric skill score, PSS, DC, and SEDI index. From them, we will show just some, like comparing the hail and maximum reflectivity. We found two similar suggestions. One is based on the critical success index and hydric skill score, which are showing the same values, and this is a radius of 2 kilometers and the reflectivity is above 56 dBz, which can be seen in this figure to the right, where on the x-axis we have a radius in every half a kilometer, and dBz starting from 47 going to 66. So in this example, A1 critical success index has a maximum value at 2 kilometers and 56 dBz. Uh, and the second threshold is suggested with a PSS and SEDI index, which says that we should use 3.5 kilometer and the reflectivity threshold above 57 dBz. And if we can check here on the right figure, we can actually see that even the critical success index recognizes this threshold as something with the highest value. However, the sheer numbers suggest this combination. But then if we check the bias table, then we can see that this option A1 actually has somewhat smaller value of bias compared to the B1. So we decided to go with a threshold of 56 dBz. And then if we check the contingency for lightning jump, we can immediately see that we don't have so many combinations. So since we are using 3x3 kilometer grid, we had only four levels of radiuses, so 0, 2, 4, and 6 kilometers. And each particular point usually cannot gather more than, let's say, 3 jumps per grid point. So we can only iterate between 1, 2, and 3 jumps. But even so, if we concentrate on the sheer numbers, we can see that the critical success index suggests the distance of 4 kilometers from the radius of 4 kilometers and value of 3 jumps per pixel to have the best score, while PSS and SETI index suggest the same distance but 2 jumps. However, if we check the values, then we can see that they are very similar. So any choice here is probably yielding something reasonably good. So we have to consult with other parameters like the probability of detection, which we show on the left figure, and false alarm ratio. Firstly, we didn't show, but to comment, so in between A2 and B2 cases, which we just show for the lightning jump, it seems that the A2 has a very low probability of detection, somewhere less than 50%, while the B2 actually has a much higher probability of detection, around 85%. Although the false alarm ratio also increases if we use this approach. But then again, as the radius increases, more and more stations which didn't report anything come within this circle, so the false alarm ratio is actually rising proportionally. And the third option, which we actually already showed on the 5th slide, is that we consider point-to-point comparison using threshold of at least 1 jump, which has relatively low false alarm ratio and relatively high probability of detection. But now we will show A1, which is reflectivity above 56, and B2 case, which considers at least 2 jumps on a location. And repeated the figure. So now we can see that there is a much less jump and the radar signal in our map, and they are mostly located near the regions where we had some hail reports. However, lightning jump does have one large region where, one large region where no hail was reported, and there is a several potential explanation why did this happen. From one side, the hail suppression network was active during that period, and it could be that it influenced on the generation of hail in this region. Second reason is actually that this event here occurred later during the day and even during the night. So it could be that the vertical profiles of temperature and water didn't favor the generation of hail. However, it did create a lot of precipitation in this region. So this suggests basically that lightning jump, as we computed it here, still has some information about rain rates within it. But within this work, we didn't check it. So this is something which will remain for the future work. So to conclude, radar assessment of hail based on the Zmax values on this particular case show actually very good results. The potential problem is scarce sampling frequency, which then leaves a lot of gaps in between, which could be carrying some information. Then Eulerian-based lightning jump offers potential information about the hail. However, it tends to overestimate the area. So improvements toward larger number of possible iterations for the contingency tables should be done to inspect in more details this event, and of course comparison with other severe weather elements which were previously proven to correlate with the lightning jump should be also assessed, like intense rain, wind gusts, water sprouts, tornadoes, and so on. So with this, I would like to thank you for your time.